And now, for something completely different. I think more than half a year ago, our dear Bart Veraert showed us something mechanical, which performed a really important task, popping a balloon when the build failed. Yeah, it has been silent for a while, but yeah, this is like the next iteration of stuff, mechanical stuff. When they came in, I thought they were going to talk about their pet rabbit, but apparently there was something else in the box.
Even kijken. Should put it a bit more here, like this. So.
It really looks amazing. After this, there's a break, so you can all come forward and have a look. But thank you both. Thank you for coming. Maxim, by the way, is working here. He's working on Apollo and now working on the consent manager. And with a bit of hope that he wants to stay on a bit longer, even in the new year. But he was telling us about his pet project, and we thought, well, this is definitely something we want to have on the SaKE. So that's why we have Wilbert and Tsoy now telling about their pet project. So guys, great, take it away.
Hello, my name is Wilbert Swinkels. I have nothing to do with programming whatsoever, but I'm very intrigued by mechanical design. It's not my profession. I'm an architect by profession, so it has actually nothing to do with this. This project I'm started, what you see is a cube solver, and it is made of FAC system. FAC system is a modular system, and this particular system was designed in the early 1950s of the last century. And there were more than 400 of these kind of modular systems designed with different success. Two of the most important, famous systems are Meccano, and you have a more advanced modular system which is called the FAC system, which is actually this kind of system. I'm just curious myself, who is familiar with Meccano? Whoa. So, I'm impressed. Well, Meccano is a beautiful system as well. You can see it on the left side. It's like the FAC system. It's a comprehensive system, and it exists from strips, beams, gears, and what you can do, you can make small machines big enough for a table. We always call it a table scale format modular system. So big enough or small enough to grip it in your hands, put it on a table, but not bigger than that. Well, as you can see, the FAC system was, like I said, designed by somebody in the early 50s, and it's much more advanced. It's actually more meant to be used by companies like Philips, at that time TNO lab, and it's much more precise. It's much more to the precise engineering standards as required at those time. Even kijken. Yeah, it was used in a lab environment or an educational environment, and they, of course, made it small machines for testing something well. For this instance, it was used as a test, a ballpoint tester. And in the middle, you can see a picture of a differential analyzer to make equations. And on the left side, you see a preliminary design of a printing press. And well, but this was all a long time ago, of course. One of the advantages of the FAC system is that it's statically very stable. It's very strong instead of Meccano. Meccano tends to be a bit, it looks strong, but it can deform You all probably have seen that. But the FAC system is much more stronger by its characteristics. So actually, quite interesting models were made by this system. On the left side, you can see a nylon spooling thread machine to study different types of spooling of a nylon thread on a spool. It was made by the TNO lab in Delft back in the late 50s. And here you can see a machine designed in the late 60s by the Philips company to design or to fabricate orthocyclic coils. Coils with a very precise setting of the copper wire next to each other. And actually this machine has been made in a series of 5 and was put in Philips factory back in Alkmaar, where they made approx 2,000 coils each day. Well, unfortunately, the system is actually mainly used in the 50s and the 60s, but in the 70s, with the introduction of the computer, it was a bit more faster to design by computer. Especially now, of course, you have several very strong software packages like SolidWorks, AutoCAD, Maya. You can create 3D models. You can even make them in a kinetical proposition, where you can even test how it should work. But nevertheless, I was very impressed by this system, and that's why I started to work with it about 10 years ago, besides my own Meccano hobby. And so in the mid-70s, the system more or less lost a bit out of sight, and people were just making use of the computer more and more. So nowadays, it's actually only used partly in the educational environment and of course in the hobby environment. And that's what I actually did. What you see here is the end result of the cube solver. But it was also quite a long process to get to this machine. I initially started with a 2-gripper solver because I wanted to make it as simple as possible, and you can make it quite small as well. And well, a 2-gripper in the X and Y axis, and below it you have some kind of positioning table. And the table you use to put the cube in the table, and then the cube is positioned well relative to the grippers, so that makes it pretty easy. Well, the table actually functioned quite well. That's why I reused it in the next concept. But as for the grippers, I was satisfied about the gripping technology behind. But sometimes, only one gripper grips the cube, and if you take, for example, the left gripper there, if that's the only gripper which grips the cube, then it might be possible that the cube is not held in position anymore. Well, that's of course killing in this kind of purpose. So that's why I made a new design based on the previous design, of course, and the new design consisted of 3 grippers. One of the important things was, of course, to position the grippers perfectly aligned relative to each other, because otherwise, you're just gonna mess up with scrambling or rotating the cube. Actually, this picture is from Aprox 210, and was just made, I think, a couple of weeks behind the first concept. They speak about rapid prototyping, but rapid in our time, I mean, this is actually crazy slow, of course. I mean, if you really want to do it rapid, then you should use a computer instead of the real physical world. Well, this machine actually proved to be pretty reliable. I was actually quite confident that this machine would bring me to a successful one. And the different components of the machine are, well, of course, the grippers itself. You have several types of grippers, but one of them is a so-called toothed gear rack gripper. In the center you see a small gear, and it drives actually the gear racks. The gear racks are held in place by two other nylon bushings. They were later replaced by a 4mm rod, which was also a FAC element. So if it's enclosed in this casing by two flanges, yeah, the gear rack can only shift in the way as you can see it. Well, there were also some, yeah, of course, in prototyping stadium, you're always looking, okay, how I'm going to make these gripping elements itself. And well, the FAC system provides a very comprehensive assortment of elements where you really can design a gripper. So at a certain moment I had this gripper where you have two motors. One motor is actually driving the gripper itself, and the other motor is driving the gripper to rotate. Actually, these are the only two functionalities of the gripper: opening, closing, and rotating. Well, in this concept, I had one motor in the satellite of the gripper, which indicates that the wiring, yeah, is also incorporated in the satellite. Well, that makes it a bit tricky, because you can only rotate the gripper, yeah, to a certain extent. Let's say 2 times 90 degrees, and then you've got to rotate it counterclockwise. Otherwise, your wiring will be just blown off the motor, and then you're just finished. So actually, I changed that concept without changing the whole machine, by the way. I only had to change the device of the gripper. And what I did is I introduced a satellite consisting of a contrate gear, which is carried by an axle from motor 0. The axle of motor 0 is all the way going through the center of the satellite, and it drives a small gear which drives the toothed gear racks. The advantage was that the second motor is not anymore placed in the satellite of the gripper, but it's placed outside. So you don't have a problem with the wiring anymore. I could have said in that time, okay, well, the program can solve it, but you can also solve it in a mechanical way. It's not always the programmer who can solve it. You can also think in a mechanical solution. And I thought this was yeah, quite an interesting solution. There's another advantage, and that comes with the weight of an object. I mean, the more weight you add to a certain object which has got to move, yeah, the more power you need to get it and to speed it up, to get it rotating and to speed it up. Lego technique, for example, has the advantage of a very low weight, so you can speed up the speed very much. And in this case, I needed some good stepper motors with stepper drivers, which could do the job pretty well. So actually, this is also the end result of the cube solver. So you see 3 grippers, the positioning table as in the preliminary concept, and what you see is also a scanner table, which moves over the cube. Further, yeah, these stepper motors don't drive by themselves. You must use a stepper driver to drive the motors. And the microcontroller, which you see in front of the machine, is actually the heart of the machine. The microcontroller sends out all signals to the stepper driver, and then from the stepper driver, the signals are sent to the stepper motors. To get the rigid structure in the machine, I added also a couple of triangular shaped parts, which actually make the structure rigid. Otherwise, it can still deform. Even in this case, even if I do it like this, if you look quite well, you can see small deformations in these grippers. So it's quite important to design a rigid machine. The basement is actually just an MDF basement made in a way that it carries the machine, and it's easy to put a top on of it, and then you can just put it anywhere you need to go. So it's quite easy to set it up. As one of the components, the two components I want to speak about is the color sensor, and that's the Raspberry. That's the microcontroller, which is the heart of the machine. First, the color sensor was actually is actually this component. I just lifted out a bit, and it originally is a color pal, but the color pal is actually just based on an analog electronic sensor. But there's an EEPROM chip and a small microcontroller on this sensor, and it works with the D-stamp program. Well, we did have a lot of trouble in making and getting it work. Several people did have a look at it, and at the end I thought, hey, let's change the circuit of the color pal. So I just got rid of the EEPROM chip and a small microcontroller. I drilled a few holes in the circuit to get some extra pins to be directed to the Arduino mini board, because Arduino mini board is a board which can get analog readouts from the color pal. Now, between the Arduino Mino and the Raspberry, we have used a logic level converter to make communication between these two boards possible. Well, of course, with the help of Maxim in this case. So here is another picture of the color sensor. Well, it's pretty difficult because these are very small parts. You can see it later when you can have a close look at it. And one of the problems was, actually it was a big issue over the time, and it was the influence of the ambient light when the color scanner tries to scan the colors. The ambient light was a big issue because it became a bit difficult to really do a good color detection. When you buy these stuff off the shelf, they always say just put it on the top of a piece of paper, and then okay, then it's no problem. Then you don't have any problem with ambient light. But in this kind of for this kind of purpose, it makes it a bit more difficult because you need to have some distance between the color pal, the color scanner, and the cube. So actually. The setup of the machine is actually like this. You have the grippers, the stepper drivers, and the Raspberry. And in between, actually this is a bit of an old picture, but I think it's, you get it. And this is in between the Arduino Mini and the Raspberry. What you see here is the logic level converter to make communication possible between the Arduino Mini and the Raspberry. The Raspberry, as you know, can only work with digital GPIOs and signals, and the Arduino Mini can work with analog in outputs. And therefore we needed this logic level converter. Actually the machine is nothing without any programming. That's just a bunch of cold metal. I'm not a programmer myself. Originally, I did have some cooperation. I did have some cooperation with the University of Amsterdam, but yeah, they seem to be not capable of making a workable algorithm to make the machine work. Well, happily I met Maxim, actually not so long ago, and well, he helped me with writing the code. Actually, he wrote the code. So I wanted to invite Maxim to finish the story.
Yeah.
Do you need this?
Yeah.
I will try to be fast.
Is this necessary? Okay. Right. So just let's get to more ephemeral things. I was doing the software part of this machine, and well, first about the solving algorithm. So as you probably know, there is quite some mathematics behind the Rubik's Cube, and it's all very interesting. It's not very complicated, but in practice, if you want to solve the cube, there is always a trade-off between the quality of the solution and the time needed to calculate the solution. So though there is an optimal solving algorithm out there, it's not very efficient because it requires a lot of brute forcing. And on the other hand, for example, the well-known three-layer algorithm is very simple and fast, but it produces solutions of 100 moves long, which is ridiculously long, considering that the longest possible optimal solution is 20 moves. So we came across this two-phase algorithm by Herbert Kochiemba and Sosam. It can give you a suboptimal solution in a reasonable time. The original implementation was in Java, and the first thing I did was to translate it to Python. But the Python version, the pure Python version, even under PyPy with JIT, it would take about 1 minute on Raspberry Pi to calculate the solution, which was too long. So eventually I gave up and translated it to C, and now it takes about 1 or 2 seconds to find the solution, which is good enough for this machine.
How much was it in Java?
In Java, I didn't test it on Raspberry, but it would actually it was faster than the pure Python with CPython, but slower than Python version under PyPy. So it's sort of, well, mainly a lot of mathematical functions and just brute forcing, so the JIT works very well. Well, I'm not going to talk much about controlling stuff because it's pretty much routine programming. Probably the most interesting part is the acceleration and deceleration, because if you're working with motors, if you want to achieve higher speeds, because of the inertia, you cannot just start rotating it on high speed right away. So you have to start slowly and then accelerate and in the end decelerate. It's not very obvious from the beginning, but it's essential in the end. So I started working on this in June, and in a month we already could solve a cube with a given initial position, but it took us 2 or 3 months more just to make the color sensing work. So this was the hardest part. The idea is very simple. We have the RGB LEDs and LDRs. We read the reflected light with LDRs, and so essentially we have the RGB values. But there are a lot of caveats, and the most difficult part is the ambient light, because it turns out that it really makes a difference if you're scanning in the dark room or under bright sun. So we started with the capacitor-based scanner because Raspberry Pi doesn't have an analog input, so you can't read the voltage from LDRs directly. So you have to make this kind of hack. So basically, we were charging the capacitor and counting the time until it reaches the logical one, which is, of course, unreliable because it's a Linux computer. You have a lot of background processes. So we had to do multiple readings, get rid of outliers, and get an average value, and the charging itself takes a lot of time. So after all, it worked, but it would take about 2 or 3 minutes to scan the whole cube, which is not very exciting. So we moved back to the Arduino. So now we're using a small Arduino board just to control the scanner, and it turned out to be I was really surprised how easy it is to connect Arduino and Raspberry Pi. You just need 2 wires and the level converter in between, and you have a serial connection. Well, I was surprised. I mean, I didn't have experience before, so I was really surprised. Of course, you have to use some kind of higher level protocol on top of that to guarantee the integrity, for example. But I found this protocol called MIN, which is designed to be used in this kind of situation. So it was perfect. So the last thing is the color clustering. So to give you an idea, this is the result of the scanning the solved cube inside the dark room. So no ambient light, but you still see that this is far from ideal. So this is red, this is actually orange, but it seems to be pink or even yellow. This is green, blue, white, yellow. So it's all very tricky without any calibrations. And we came up with 2 possible approaches to do the clustering. The first one is the range-based, simple one. It didn't work out because it was impossible to do this under different ambient conditions. And the other thought was to use some of those clustering algorithms, but it didn't work out as well because most of them are probability-based, and they give you a decent result, but not the exact one. So in the end, we were doing these things. So we first do some artificial calibrations for each of the color, for each of the facelet positions. And then we translate RGB to HSV to locate the white cluster, because white is a special color. You have to handle it differently. And then we increase saturation. This is very important because it will also help us to fight the ambient light. We increase saturation for other colors, and then we compare the values to the central facelets, because we do know that all the central facelets are different colors. Yeah, so this is pretty much what I have, and we can get to the demonstration and to the break. So I think we can just I don't know, how do we do that? Probably switch this one.
Yeah.
And by the way, if somebody has any questions, you can ask, of course, while we're. Yeah.
Actually, none. Well, there was a very small issue when the cube was held in position by the grippers, and when the table closed. Sometimes it occurred that the cube was a fraction lower than it should be. But I placed two black plates on the upper side of the positioning table. And then that problem was solved as well. So actually it was, that was actually one of the most easiest thing over the time. Okay, well, I just have to look that this is of course a good. The strange thing is that actually you should think it's perfect. It's a perfect cube.
This is the first time we present it to someone in live, so if it doesn't work,
Sure. So the first time we always look, because we traveled a bit with the machine of course today, just to have a look if the grippers grip the cube properly, and it looks very solid. And
Yeah,
because if you have one step losing, I mean it can go wrong of course. And if you think it's okay, then we just start the operation. It's always an exciting moment.
oh,
It's a bit strange.
yeah.
The table should
Yeah.
have closed, but
That's why we have this handle.
and actually, well, actually, this never occurred. Actually,
Yeah.
that the table
It's a
didn't
demo
close.
effect.
It's a demo effect, yes. So actually, that's it. This one was pretty
Yeah.
fast.
Sorry? Yeah, it is solved. Yeah, it's easy.
Questions?
Why didn't you use a webcam or something to find the colors?
Good question.
It's a very good question. Well, we are going to use a webcam actually too for the next generation. But when I started this project, I mean 6 years ago, I only used the Arduino as a start off. I bought some off-the-shelf color sensors, lots of toggle, and I did like the old-fashioned way of just scanning the cube. I think it really fits with the retro look of the modular system. But in the next generation, we are now working on the next generation, which will be a 4-gripper. Will be way more faster, and then we're going to use cameras. So that the cube is, the faces are all recognized in a split second.
How many man hours are in this?
Well, you would be amazed. I mean, I just told you that I started it back in 2009, but of course I didn't work all the time. This concept, except for these two motors, outplays, but the second concept was just made in a couple of months. And actually that was the basis of this concept. The only changement was of course to outplace one of the motors out of the satellite. Well, the layout of the stepper drivers changed a bit. I used to have the stepper drivers a bit more down, but I put them all together to make it a bit more voluminous machine and close to the stepper motors as possible. The color sensing part was actually, that was a real issue. I met many problems, in making a workable. But it's funny that, when you actually see how it did it now, then you almost should think, why didn't you do it immediately? No, really, really.
Okay, other questions? I'll come to you.
Are you interested in the cubes in other shapes, like the dodecaeder and yeah? You're working on it.
You also have this cube. It's called 17 rows and columns. It's quite well. That could be a challenging machine to make to solve that one.
Welcome to do.
So a couple of months ago there was a competition for humans to solve this Rubik's cube. Do you also have a competition for machines, and do you plan to enroll it?
Yes, there is a competition. Currently the world record, I believe it's 3.5 or so.
With scanning, it's 5.6, I think.
No, they are doing the scanning in these three, yeah.
In the 3.5?
Yeah.
Okay.
It's 3.5 or something like that. It's sold by another machine made with Lego parts. Yeah, it's called Cube Stormer 3. And yeah.
It's a four gripper one, but it's
Yeah,
amazing.
yeah,
They
it's-
really did do
it's
an
cool.
amazing job. I mean, I was very surprised because I saw the first generation of this machine, which was actually quite a voluptuous machine, actually standing on a standard and in the air, and you saw it a bit vibrating a bit during operation. But when I saw the second generation of it, it was very impressive what they did. I mean, they really made a compact machine, well use of the Lego parts, and crazy fast. I mean, I was very much impressed, not only by apparently a very good algorithm, but also by the machine design. Absolutely.
Just for the protocol, these motors can move faster. So because it's obvious that we cannot break this record with this kind of a scanning and stuff. So we try to make it more, to be like pleasant to see. So we made it a little bit slower so that you can see every move, and yeah. But I think in the second generation we will try to compete with those.
Really cool. Thanks, guys. We have a small break, so if you have any questions for Wilbert and Maxim, talk to them during the break. Okay, thanks.